I don't think that a hypercomputer is possible because it violates what's possible. It basically requires that you are performing infinitely many steps in a finite number of steps, finite number of transitions. That you would have a transition in there that is a single step is manipulating an infinite amount of information. And I basically belong to the camp that doesn't think that's possible. But there are other camps which think that it is possible. And there's also a large part of the physics community and even of the mathematics community who doesn't worry about it too much and thinks it's not an issue. But to me, it appears that it is. Basically, when I look at this, it seems to be quite obvious. And you would, basically a hypercomputer, most definitions of a hypercomputer would violate Turing's discussion of the halting problem. And let's look at what the halting problem is, right? The halting problem is this issue that for a Turing machine, for a computer that runs a certain program, you cannot, in the general case, decide in advance whether the program ever comes to a halt or somehow enters some kind of infinite loop, or performs a process that never ends and always never converges basically to a finite result. And that you can do this in many cases. You can often find that this program will always halt if you completely understand it, but you cannot do this in the general case. And the reason why we define programs in such a way that they halt, I think, happened because when the Turing machine was defined, it was defined to implement classical mathematics. So the idea was you have a function in classical mathematics. We want to find a foundation of classical mathematics in a theory of machines. So we define an abstract, hypothetical mathematical machine that gives you a result of a function that does so by taking an initial state, that is the configuration of a tape in the Turing machine. And that is a translation of the arguments, the parameters of the function that you want to compute. And then you have a procedure that changes the state of the tape until it finishes it, until it gets into a final state, and the configuration on this tape is going to give you the result of your function. And in classical mathematics, you can define functions that take in infinitely many arguments and give you back infinitely many values in a single function definition. Right? That's very elegant. You can have something that takes in the set of all sets. It's a very nice function to have that consumes the set of all sets and tells you something about the set of all sets after having looked at each set. And so this definition exists in this hypothetical Turing machine, and you could say, oh, well, unfortunately, but we can physically realize in our universe is only limited to finitely many steps and a tape of a finite length. But it's maybe just a limitation of our own universe. There could be other universes where this limitation doesn't apply. Or maybe we can use quantum mechanics or some other weird trick to make it happen in some sense. And the discussion of the halting problem shows that the assumption that you could build a machine that determines whether the program halts, which means some machine that is able in some sense to perform that infinitely many steps, leads into contradiction. So it cannot exist. And that implies, I think, that in no mathematical universe can you build a machine that preserves the semantics of classical math, that is going to give you a function over all the sets, and after having looked at each set gives you the result. But of course, you can make an abstraction. You can talk about a general property, about what it means to be a set, and then compute over that property. But you will not be able to look at the parts itself, right? So you can define a symbol that you call infinity, and you assign certain properties to it, and then you make inferences over those properties. But they don't happen because you looked at infinitely many elements.